Hello, everybody. Hello, everybody. Good morning, good afternoon, good evening, good night. Welcome to our seminar. Can you hear me? Okay, so today we have our guest, the speaker for today is Professor Jacob Mostovoy from Mexico. He will speak on the Chevalley-Eilenberg complex for Leibniz and for Sabinin algebras. Okay, please, Jacob, you can start.
Thank you. Well, thanks a lot for inviting me to speak here. It's a wonderful seminar. I enjoyed it very much. So I'm going to talk really about definitions. So it's nothing very profound, but these definitions are kind of well, it's always important to have correct definitions. So I think it's worth dedicating a talk to it. This is part of a long ongoing project with Ivan Pavel Shestakov and Jose Maria Perez Izquierdo. Basically, we're trying to understand how Lie theory works in the absence of associativity. And this is why I'm talking about Sabinin algebras. So as part of developing Lie theory, it would be nice to understand the cohomology for Sabinin algebras. Now, understanding cohomology is difficult because there are so many versions of it. So, for instance, there are very many flavors of Sabinin algebras, and in principle, each of these flavors can have a specialized cohomology theory. So, one of the paths to cohomology is via the Chevalley-Eilenberg complex, and it turns out that it's a geometric object in its own right. So I'll try to focus on the Chevalley-Eilenberg complex rather than cohomology. Actually, cohomology is all about modules, but I will speak about, when I speak about cohomology, I will always speak about cohomology with trivial coefficients. So so basically, I'm going to talk about two definitions. One is the definition of one possible definition of cohomology for Sabinin algebras, and the other one is a definition for is an explanation of what a Leibniz algebra is. And these two subjects, they may seem to be quite different, but it turns out that they're very closely related. Well, especially since we're operating on the level of definitions. So let me first remind you how Lie algebra cohomology works. Well, in its most basic features. Again, there are many ways towards Lie algebra cohomology, and it's important to choose the right definition so that it will generalize painlessly. So Lie algebras, well, at least initially, they appeared as a tool for the study of Lie groups. So one of the possible motivations for the study of Lie algebra cohomology is to study the cohomology of Lie groups. And the thing is that if you have a compact Lie group, well, a Lie group is a manifold. So in order to calculate the cohomology of a manifold, you can use de Rham cohomology. And of all the differential forms on a Lie group, we can restrict our attention only to left invariant differential forms. Well, this is because of compactness. You can use an averaging trick, so you can average differential forms, you can project them onto left invariant differential forms, and they will give you the same cohomology. And since each of these forms is determined by its value at 0, really this whole question reduces to the study of a certain complex defined in terms of the Lie algebra of your Lie group. So the complex of left invariant differential forms explicitly is written like this, and the square brackets that appear in the expression for the differential are the brackets of the Lie algebra of your Lie group. So this only depends on the Lie algebra, and by definition, this is the cohomology of a Lie algebra G with trivial coefficients. So another approach to cohomology is via derived functors. So we can take an acyclic resolution of the trivial G module by 3 G modules, and then well, taking the hom from this resolution, we get a chain complex, which the cochain complex, which calculates the cohomology. So the question is how to get the resolution, and the Chevalley-Eilenberg complex is a certain particular type of this resolution. Now, there are different types of terminology. Sometimes people speak about the Chevalley-Eilenberg algebra as the standard complexes, which consists of the exterior powers of the dual of your Lie algebra. But I'm following the terminology of Charles Weiber. So he uses the words the Chevalley-Eilenberg complex for this free resolution. So we only need, in order to calculate the cohomology of a Lie algebra, we only need this Chevalley-Eilenberg complex as a G module. But it turns out that in fact it has more structure. It's a differential graded Hopf algebra, and this is the main point of my talk. So let me just remind you what differential graded things are. So differential graded Hopf algebras, and well, here I've written down the definition of a differential graded Lie algebra because we're going to see more of them in this talk. So basically, a DG Lie algebra is simply a Lie algebra in the tensor category of chain complexes. Well, a tensor category is a symmetric monoidal category. So everything, all things multilinear work in the same way as for vector spaces, with the only difference that we have this funny braiding. I mean, the braiding which interchanges factors in the tensor product. In the differential graded case, in the case of chain complexes, it involves some signs. So the definition of a Lie algebra in this category requires some funny signs all over the place, and well, we'll only look at DG Lie algebras which are 0 in negative degrees. So there are two conventions for DG Lie algebras. Some people prefer homological grading, which means the differential going down, and some people prefer the cohomological grading with the differential going up. So I consider the differential going down. I don't know. I mean, I learned about DG Lie algebras in the paper of Quillen on rational homotopy theory. So this is why I use homological grading, basically. So the most trivial example, the really trivial example of a differential graded Lie algebra is this. It comes if you have a normal Lie algebra, we can convert it into a differential graded Lie algebra just by placing it in degree 0. So there are no signs involved, of course. And well, this is a really trivial example, and it's not worth talking about it. A slightly less trivial example, which is actually an extremely interesting example, looks very similar. You take a Lie algebra and you place 2 copies of it into your chain complex. In degree 0, we have 1 copy, and in degree 1 we have another copy. And the differential here is the identity. So it's called nowadays it's called the cone of the Lie algebra. So the structure of a DG Lie algebra here, well, in degree 1, obviously the copy of G in degree 1 has a trivial bracket on it because it lands in degree 2, and degree 2 is 0. So the only thing we have to specify is the action of G in degree 0 on G in degree 1. So this is just the adjoint action. So the Chevalley-Eilenberg complex then is just the universal enveloping algebra of the cone of G. This is probably the simplest way to construct it. So again, we're in a tensor category, so everything works as it would work for vector spaces. You have universal enveloping algebras for DG Lie algebras. You have Poincaré-Birkhoff-Witt theorem. So the only thing we have to note is that the cone on G is actually acyclic. We have a differential graded Lie algebras with 0 homology. And it turns out that the universal enveloping algebras for differential graded Lie algebras, they commute with homology. So the universal enveloping algebra is also acyclic. And well, it's easy to check that. This differential graded Hopf algebras that we obtain. Well, I just remind you, just in case, that the universal enveloping algebras are Hopf algebras. There is a coproduct coming from the diagonal map, basically. Okay, so it's easy to see that this is actually a free resolution, and it's the same thing as the usual Chevalley-Eilenberg complex. So this seems almost trivial, but it's actually quite profound. I mean, this is not the way the Chevalley-Eilenberg complex is usually defined in textbooks. But of course, this fact is known to many experts since a long time ago. Although finding the first reference for the statement is quite impossible. So let us have a look at this construction from a different point of view. So the construction of a universal enveloping algebra is actually something non-trivial. So my favorite way of constructing the universal enveloping algebra is the way it was done by Serre in his book on Lie algebras, or in Bourbaki, in the volume of Bourbaki on Lie algebras. It appears in this fashion. So if we have a Lie group the product is simply a map G cross G to G. And if you look at functions, I mean, I write here the space of functions. I just don't want to get into details. So it kind of works in some way. So this product induces a kind of a coproduct on the space of functions. The only thing is that, of course, it doesn't go to the tensor product, but it goes to some completion of the tensor product. But still, it looks like a coproduct. And then, so we have a coproduct on the space of functions, and if we consider the space of distributions on G, which is linear functions on functions, and we want to then we get a convolution on the distributions. Now, here we will be interested in distributions which supported the unit of the group. And these, more or less by definition, we don't want to get into analytic details about the space of functions. So we just consider the Dirac delta and its derivatives. Then the coproduct on functions gives us a product on these distributions. And the diagonal of the group gives a coproduct on distributions. Now, the space of distributions, it was supported one. It doesn't really depend on the product of your group at all. So the space of distributions with supported one is basically the symmetric algebra on the tangent space at the unit. We don't need to speak about Lie algebras here. So it's a symmetric algebra because we have the Dirac delta, which is the constant, and then the directional derivatives of the Dirac delta give you the generators of the symmetric algebra. Okay, so the observation by Serre is that this is the universal, this distribution algebra with convolution is the universal enveloping algebra of your Lie algebra. So this is a wonderful construction. And one thing that is particularly pleasing about it is that we don't need to know what a Lie algebra is in order to construct its universal enveloping algebra. We get this universal enveloping algebra directly from the group. So let us replace functions in this construction by differential forms. So it will work in the same way. We have the product. The product induces some kind of a coproduct on differential forms. And then instead of distributions, we take what's sometimes called currents. I mean, it's called currents in geometric measure theory. I mean, the word current has too many meanings, but it is often used in this way. So distributions which are linear functionals on forms rather than functions. Well, they also form a Hopf algebra, and well, this is just the Chevalley-Eilenberg complex of your Lie algebra G. Again, we don't need to know what G is, which is we have the Lie group, and directly we get the Chevalley-Eilenberg complex. So there is another way to look at it. I mean, these are all the same things, but this is just another way to look at it. So if we have a Lie group, you can think of its tangent bundle as a differential graded manifold, so to speak. I don't want to say anything about differential graded manifolds. Just imagine that it is one. So the tangent bundle of a Lie group is again a Lie group, and its Lie algebra is going to be the cohom on G. So the distributions on this Lie group, on this differential graded Lie group with supported one, is the same thing as the Chevalley-Eilenberg complex. Okay, so here is the key observation. we never ever used associativity of our group. So you can take any product. In particular, this product can be non-associative. So this, by the way, gives you many things at once. It gives you a universal enveloping algebra for a Sabinin algebra. Sabinin algebra is an analog of a Lie algebra for an arbitrary non-associative product. So you get a universal enveloping algebra for a Sabinin algebra, and you also get the Chevalley-Eilenberg complex for a Sabinin algebra. So, well, half of the talk is already covered. So the product on your Lie group is not necessarily should not necessarily be global. We're only interested in what happens in some neighborhood of the unit in G. And for Lie groups, it's not really important because any local Lie group integrates. It can be extended to a globally defined group. In the non-associative case, it's extremely important because most of the, most, I would say, interesting loops, most interesting non-associative products, they're only locally defined. They're not globally defined. So non-associative products appear, for instance, on homogeneous spaces. This is the main source of non-associative products is on homogeneous spaces, and it's there is a canonical way to construct it, but it's always going to be local. Also, I mean, if you don't like to think about homogeneous spaces, I mean, when you think of the Cayley-Dickson process, for instance, in dimension 16, you don't have a globally defined loop, but you have a local loop, which works perfectly fine. So this construction works in the local case. Actually, we didn't even really need a unit here. So it's good to have a weak unit, which is like 1 by 1 is 1. This is kind of probably necessary for this construction, but not more. So why am I interested in this kind of exotic products? Well, there are some interesting products that are not that are weakly unital but not unital. So one of these products is provided by conjugation on a group. So conjugation on a group is weakly unital but not unital. And another kind of products like this comes from considering the non-associative products. I mean, so in non-associative, in local loops basically consist of 2 parts. So one part is right alternative, and the other part is just wild. I mean, it satisfies nothing. So this other part is only weakly unital. So this is an interesting thing, though I'm not going to say anything else about this kind of products. And then there is another thing that is going to be useful when I speak about Leibniz algebras. So the construction of the Chevalley-Eilenberg complex comes in 2 steps. We take a Lie algebras and replace it by its cone, and then we take the universal enveloping algebra of the cone. So there are actually many interesting functors from Lie algebras to differential graded Lie algebras. And well, I mean, we'll see one later. So it kind of makes sense to replace the cone by something else and ask, what does the universal enveloping algebra give you? And well, I can tell you what it's all about. If there is a completely natural differential graded Lie algebra associated to any Lie algebra, or actually any Leibniz algebra. And if we take the construction of the Chevalley-Eilenberg complex with this cone, then we get Leibniz homology instead of the usual homology. So let me talk about Sabinin algebras a little bit more. So I already told you how to define the Chevalley-Eilenberg complex for Sabinin algebras. But let me tell you what Sabinin algebras are. So we have different. Sabinin algebras is a kind of a general name for tangent structures to all sorts of non-associative products. So when you're talking about Lie groups, your Sabinin algebra is going to be Lie algebra. For Moufang loops, it's Maltsev algebra. For Braque loops, we have Lie triple systems. Well, normally people think of Lie triple systems as tangent to symmetric spaces. So any symmetric space locally is a Braque loop. So local ball loops give rise to ball algebras, then right alternative loops give something which is already general enough. And these are the flat Sabinin algebras. So the word flat here means that they come from flat connection. It's not any other kind of flatness. So the top line of this table is a bit of a miracle. So a Lie group is a very non-linear structure, and Lie algebra and the structure of a Lie algebra is something much simpler, at least on the face of it. So it's a bit of a miracle that the Lie group is encoded completely, or at least up to a covering by vector space with a bilinear product, satisfying some really simple identity. So while we go down along this table, somehow the miracle starts waning. So the correspondence between Moufang loops and Maltsev algebras is still also quite impressive. Ball algebras already have two operations. I mean, one operation is not one bilinear operation is not enough to encode the product. So we need one bilinear and trilinear operation to encode the ball loop. And Sabinin algebras, they're already a total mess. So they have an infinite number of operations which satisfy some extremely complicated identities. Now, these extremely complicated identities are really artifacts of the way that we write things down. But anyway, what I want to say is that we cannot really expect a general Sabinin algebra to be of much help to study an arbitrary formal loop, formal or local loop. I mean, I say formal here because Sabinin algebras, since they have an infinite number of operations, you have questions of convergence there. It's quite complicated. But anyway, a non-associative product, an arbitrary non-associative product, really involves no restrictions. So you can write a unital non-associative, a local non-associative product without thinking at all. There are no restrictions. So you can't really expect that a tangent structure to something like this will miraculously give you more information. So Sabinin algebras, they're just kind of derivatives of arbitrary functions. So it's not, we don't expect miracles there. So let me tell you the definition. Let me tell you several definitions. So this is the last definition that was given by Sabinin. Sabinin gave three definitions. Two of them were with Mikheyev. This is the third definition that appears in his book. And a Sabinin algebra is a vector space with two operations, which satisfy these very simple identities. So this first operation D is something like antisymmetric. It's not antisymmetric. You just know that D of x and x is 0. And the second operation that he calls multi-operator, well, it's some kind of a generalized conjugation. So the catch here, this looks like a simple definition, but the catch here is that these operations are non-linear. So this is not algebra we're doing here. It's not, we don't know what to do with non-linear operations. Now, in order to convert it into algebra, we have to assume that there's some kind of power series, that they're polynomial, something like this. So these can be thought of as products on the tensor square of the symmetric algebra of V to V. So in order to obtain, well, I'm not going to tell you how these operations are obtained. It's a geometric procedure which is quite similar to what is done for a Lie algebra. It's basically comes from the fact that structure constants for a Sabinin algebra are not constants anymore. They are functions, and these functions are give rise to these two operations. So in order to obtain some multilinear operations, what we do is we expand these two operations into power series and then multilinearize it. There is a standard procedure for that. And we get some identities which are artifacts of multilinearization. And these identities are horrible. So this is the first definition of a Sabinin algebra that appeared. This is still a definition that many people use. And I'm not asking you to try to understand it. I just want you to appreciate the horribleness of it. It really is a bit difficult to work with. Although it's not impossible. So there are many works on Sabinin algebras, very meaningful works that use these identities and deduce some non-trivial facts about Sabinin algebras. So this is only half of the definition. This is a flat Sabinin algebra. And the general Sabinin algebra is a flat Sabinin algebra together with another sequence of operations with two indices. Well, dreadful. So a much nicer way of thinking of Sabinin algebras, well, I will speak about flat Sabinin algebras from now on, because this second operation, it really has no information in it. It's completely symmetric in all variables, so we can choose it arbitrarily somehow. So a nicer way to think of Sabinin algebras is in terms of Lie algebras. So if we have a Lie algebra G, which is decomposed as a sum of two vector spaces, one of which is a subalgebra, then the complement of the subalgebra has a structure of a Sabinin algebra. Now, this is the way we define multilinear operations on it. These are just projections of the iterated commutators. And so if we define these operations, these parenthesis operations, as projections of commutators, then the antisymmetry of the Lie bracket and the Jacobi identity translate into these two identities. But then there is another identity, the more interesting identity, coming from the fact that H is a subalgebra. So if we have a subalgebra, then that means that the commutator lies in the subalgebra. Again, well, the Lie bracket of two elements of a subalgebra lie in the subalgebra again, and this is expressed via the fact that the projection equals to 0. So here we have an identity. We have the other series of identities satisfied by these operations, and well, they're not very simple either, but they're a bit more palatable than the initial identities of Sabinin and Michaev for the bracket, for the angular bracket operations. So the third definition is to imitate, is to put these identities as the defining identities of a Sabinin algebra. And for any Sabinin algebra can be realized as a complement of a subalgebra in some Lie algebra. And this construction is functorial, actually. I have to say that there is more than one Lie envelope for a Sabinin algebra, but when people talk about the Lie envelope, normally they speak about the minimal Lie envelope. We'll see later the examples of other envelopes. So one interesting things about the Sabinin algebras is that the primitive elements in any non-associative bialgebra have a structure of a Sabinin algebra. And again, really, there are two operations. There are two important operations, which are the commutator and the associator in any algebra. And these two operations, they preserve primitive elements. This is quite similar to the case of Lie algebras, but with this new operation, which is the associator. And the thing is that the commutator is a derivative. I apologize. The commutator is a derivation, but the associator is not. So we can try to force the associator to be a derivation in each of its variables. And this way we define these operations that measure the failure of the associator to be a derivation. And so there are three of these operations, but we really only need two. I'm sorry. So each of these operations actually also fails to be a derivation in each of its variables. So we can repeat the procedure, and this way we get an infinite number of operations. So this is how a Sabinin algebra. Sabinin algebras are related to Hopf algebra, to non-associative Hopf algebras. And as it was first shown by Pérez-Izquierdo, each Sabinin algebra has a universal enveloping algebra. And well, actually, it's an algebra. It's the argument of Pérez-Izquierdo was algebraic, but we can use the geometric argument and just observe that this is the algebra of distributions which supported the unit of the corresponding formal loop. So in this very way, we construct out of a Sabinin algebra, we construct a Chevalley-Eilenberg complex. So again, it's one of these ways that I indicated for Lie algebras. Either you look at the algebra of functionals on differential forms with convolution, or you can define differential graded Sabinin algebras and take the universal enveloping algebra, which is probably not what you want to do. So here one interesting thing is the following. So the Chevalley-Eilenberg complex, it only really depends on the, well, as a chain complex, it only depends on the underlying vector space, because it's dual to the differential forms. It's only the product that varies with the product of your loop. So we can write the Chevalley-Eilenberg complex in the same way as for Lie algebras, but it does not seem to be a free resolution by left modules over the universal enveloping algebra or Sabinin algebra. So here's a catch. I mean, we don't really know. I mean, I'm kind of hesitating, saying it does not seem to be a free resolution. Well, the thing is that we don't really have good theory for non-associative modules. I mean, we have the definitions. Of course, it's easy to give a definition, but it's not clear how meaningful that would be. So also for Lie algebras, a module over a Lie algebra is the same thing as a left module over the universal enveloping algebra. Here we can't say that. Here things are more complicated. So we have the Chevalley-Eilenberg complex, which is not a resolution, but still, I mean, nobody prohibits us from using it in order to try to define some cohomology. So let us consider this space, the maps from the Chevalley-Eilenberg complex to real numbers. I mean, we think of real numbers as the trivial module over the universal enveloping algebra of your Sabinin algebra, and we want those functions which vanish on the left coset of the non-trivial elements of your universal enveloping algebra. This is kind of the module structure that we can, the simplest module structure that we can expect. So, well, what we obtain is something quite meaningful. So this is the complex of left invariant differential forms on the local loop, and the left invariant differential forms on a loop are defined in the very same way as on a group. Okay, so this is something extremely meaningful, and it tells us immediately that we get something non-trivial because there exist compact loops, non-associative loops, and therefore they have cohomology, and this is the cohomology that this complex calculates. So still, it's a kind of an interesting complex. I mean, it's not the exterior algebra on the dual of your Sabinin algebra. It is strictly smaller. So in many cases, for instance, the term of degree 1 is the maximal Lie algebra quotient of your Sabinin algebra. So this complex can be calculated in terms of the Lie envelopes. So this universal enveloping algebra of a Sabinin algebra can be at least up to some extent, to a great extent, reconstructed from the universal envelope of the Sabinin algebra. So we can think of this universal envelope of this universal enveloping algebra of the Lie envelope of a Sabinin algebra as some kind of a left multiplication algebra. So let me move faster. So what we have is that we can interpret these this complex that we get basically as invariant forms on the homogeneous space of G modulo H. So this is something extremely classical, and it might be even a bit disappointing that we were doing some non-associative algebra and we got back to something classical from homogeneous spaces. But let me remind you, we're doing the most general theory possible. So if we develop the theory of the representation theory or cohomology theory for, say, Maltsev algebras, we can expect some interesting phenomena that are related to the octonions, let's say. But here we're playing an extremely general game, and we cannot expect anything very interesting. Let's put it this way. So, of course, there are cohomology theories already for some particular classes of Sabinin algebras, and the Lie triple systems is probably the most interesting game to play because they're relatively easy to study. So let me remind you, a Lie triple system is a vector space with a trilinear product, and the generalizes this trilinear product generalizes the double bracket on a Lie algebra. So Lie triple systems come from algebras with involutions, from Lie algebras with involutions, and actually for each Lie triple system there are two special Lie algebras which contain it. One is the universal envelope of a Lie triple system, and the other one is the standard envelope. So these envelopes, they form a category, and one of them is initial there, and one of them is terminal. So there are at least 3 cohomology theories for Lie triple systems, and none of them seems to be the same thing as the Sabinin algebra cohomology. So Harris cohomology and the cohomology of Hodge and partial, they're defined in terms of the standard envelope of Lie triple systems. I don't really want to say anything about this, apart from the fact that the Hodge partial cohomology really seems to be the right cohomology, in the sense that it has an intrinsic definition in terms of Lie triple systems, and it really is a derived functor in the very same way as Lie algebras are. Lie algebra cohomology is a derived functor, but somehow the Chevalley-Eilenberg complex does not give the resolution for these modules. So the strangest cohomology of all is probably the first of them. It's the Yamaguchi cohomology. So Yamaguchi defined it in 1960, but then it turns out that it can be interpreted in terms of Leibniz cohomology. So Yamaguchi cohomology of Lie triple systems is probably the first appearance of Leibniz cohomology ever. So what happens is that if you have a Lie triple system, then its tensor square is a Leibniz algebra. And we can take its Leibniz cohomology with some quite non-trivial coefficients, and this way we get exactly the Yamaguchi complex. So this brings us to the second subject, for which I have like 10 minutes. And this is that of Leibniz algebras. So a Leibniz algebra is basically a non-antisymmetric version of a Lie algebra. And for each Leibniz algebra, we have, of course, we can antisymmetrize it and get a Lie algebra. So there is an always a short exact sequence. If G is a Leibniz algebra, it maps into its universal Lie quotient. And then there is the kernel, which is the ideal, which is linearly generated by the elements of this form. So there's been lots of activity on Leibniz algebras in the last 30 years. And it's kind of, I mean, the whole theory of Leibniz algebras leaves kind of a strange impression. It looks like a theory of Lie algebras, but slightly weaker and somewhat less useful, let's put it this way. And well, many people are interested in Leibniz algebras. Many people are critical about Leibniz algebras. So the fact is that Leibniz algebras exist, and they have some properties. So in this situation, there should be a reason why they exist. And the reason why they exist, I forgot to mention the Leibniz algebra cohomology. I'm sorry. So I apologize. So the Leibniz cohomology, I'm sorry. Leibniz cohomology was probably the main reason for Lade to introduce these things. So the complex for Leibniz cohomology is exactly the same as for Lie algebra cohomology, but instead of the exterior powers, we take tensor powers. And this is probably justified by the following formula. There's a formula of Lade and Quillen proved by Tsigan for the homology of the Lie algebra of matrices over any algebra. And there is a version of it for Leibniz homology, which instead of cyclic homology uses the Hochschild homology. So this is the interesting thing about Leibniz algebras. But okay, so let me go back to the definition. So the Leibniz really, what turns out to be the case, and this is actually absolutely implicit in the works of Lade himself, together with Pirashvili. They understood this fact, but somehow they didn't like it, so they just swept it under the carpet. So it turns out that Leibniz algebras are just a piece of structure of differential graded Lie algebras. So if you have a differential graded Lie algebra, then in degree 1 you have a bracket. You have a derived bracket, and defined in this way. So on the left-hand side you have the Leibniz bracket. On the right-hand side you have the bracket in the differential graded Lie algebra. And it turns out that every Leibniz algebra is obtained in this way. So it's very strange that this observation was not explicitly made by Lade. He gave tons of examples of Leibniz algebras, probably all the examples apart from this one. And it started, and somehow after 30 years, people started realizing that this is the case. I mean, you can find this observation in many papers by some physicists, by Jim Stashev and co-authors. So this is actually elementary, but strangely it was completely missed for a long time. So let us consider the DG Lie algebras such that which start with a Leibniz quotient. In degree 1 you have a Leibniz algebra. In degree 0 you have its universal Lie quotient. Then this functor that sends a differential graded Lie algebra into Leibniz algebra has both right and left adjoints. And the right adjoint is the minimal DG algebra, we call it. So this is basically, this is simply this short exact sequence, three-term exact sequence. You have to define the brackets. You have to define the brackets, but it's not very difficult. So this is how you do it, and you get a DG algebra out of Leibniz algebras. So actually, Leibniz algebras are DG algebras of this form. There is nothing else to the Leibniz algebras really. And a cone of a Lie algebra is an example of such an enveloping DG Lie algebra. So we have an acyclic DG Lie algebra, and we can take its universal enveloping algebra. And well, this will not give us Leibniz homology though. It gives us another way to calculate the cohomology of the maximal Lie quotient. Leibniz algebras actually have more representations than Lie algebras. So in the case of non-trivial coefficients, we can have something beyond the cohomology of the Lie quotient. But the left adjoint to the Leibniz functor is more interesting. It's something we call the universal enveloping DG Lie algebra. So basically, we consider the Leibniz algebra as a chain complex of length 2, take a free algebra and quotient it by the smallest relations that we have to. So this way we get something which can be described explicitly. And if we take the universal enveloping algebra of that, then we get the Leibniz cohomology. So that's probably the least unpleasant explanation of the Leibniz cohomology. And so it works with all sorts of coefficients. It's the right way to construct the Leibniz cohomology. Now, one unpleasant thing is that this universal enveloping algebra is not acyclic, because that's how it works. But well, what can I do about it? So I will only mention in passing that this point of view on Leibniz algebras via the differential graded Lie algebras is actually useful. So a year ago, maybe a couple of years ago, Pirashvili published a conjecture, and he explicitly said that it took him that he worked on it a lot. He asked several clever people, and they couldn't do anything about it. And well, it turns out that using the DG Lie algebra techniques, this conjecture is really easy to prove. So this is the proof. I mean, it's not very long, and it involves the definitions. So okay, so this is actually all I have to say today. And well, thank you for your attention.
Okay, thank you very much, Jakob. Let us thank Jakob. Now, questions or comments, please.
Hello, may I ask a question? Hello?
Yes,
Sure.
you can.
So I understood correctly that Leibniz algebra comes from DG algebra.
Mm-hmm.
So, what's the idea of DG algebra?
Sorry?
What's the idea of the proof? How you can construct DG algebra for given Leibniz?
Okay. Well, I mean, let me go back. I mean, these are absolutely explicit constructions. So.
Bueno, ahora va a pasar el verano, el invierno ya que es muy timor, mucho más.
So one of these DG algebras, the smaller DG algebra, is just the Leibniz algebra. So this is degree 0, this is degree 1, and this is degree 2. So and these are all the brackets. I mean, this is the explicit definition of all the brackets in this DG Lie algebra. Now this is the smaller DG Lie algebra. The universal DG Lie algebra is defined here. So it's, you take a free Lie algebra, you take the vector space, the differential graded vector space with G in degree 0, G in degree 1, and you take a free differential graded Lie algebra on that. So it's a very big algebra, and even when you take these relations, so the relations are that you want your brackets. You want your bracket on the DG Lie algebra to be compatible with the Leibniz bracket. This is all. So when you take the quotient, you still get something like a free Lie algebra on a vector space of degree 1. So it's a big thing. But this is explicit definition. I hope this clarifies things.
Thanks a lot.
Okay.
You know, probably another question. You mentioned DG manifold. Yeah. For Sabinin algebras, can you construct some kind of DG manifold?
Well, for Sabinin algebras,
For the types. For Leibniz, I guess if you take this DG, you can do something.
Okay, so the DG manifold here is actually, I mean, it's not even necessary to say that it's a DG manifold. It's just the tangent bundle of your Lie group. So the tangent bundle of your local loop is going to be a differential graded local loop. So yeah, of course, all the same construction works.
The same thing. Okay, thanks a lot.
Okay. More questions? Comments? No questions. No questions and comments. So let's thanks Jakub again for very nice talk. Okay, and now I want to make announcement. For the next Thursday, we will have a talk by Raimundo Iluani from IMPA, and he will speak on the singular support of the Ising model. So see you the next Thursday. Thank you everybody for participation, and thank Yasha again. Спасибо. Till the next Thursday. Bye-bye.